Get ready to unlock the invisible force shaping the tech around you. Magnets are everywhere. Inside your phone's speakers, your laptop's storage, and in life-saving hospital MRI machines. Here's a mind bender. Break a bar magnet in half, and you don't get a single north and a single south. Each piece becomes its own tiny magnet with both poles. Stick around to see how magnets are actually made. Now let's step into the foundry and watch how magnets come to life. First up, raw materials and alloy design. Not all magnets are the same. Some occur naturally, like lodestone used by ancient sailors as a compass. Others are permanent magnets that keep their strength after exposure to a strong field. And then there are electromagnets, which create magnetism only when electric current flows through a coil. Industrial magnets come from carefully engineered alloys, like alnico, aluminum, nickel, and cobalt. Add-ins such as copper, iron, or titanium fine-tune the performance. The recipe matters. Even small changes can weaken the magnet, hurt high-temperature stability, or reduce durability. Next, the casting process. With materials chosen, a mold is made, usually sand, because it's inexpensive, durable, and can handle extreme heat. A pattern goes into a machine that packs sand tightly around it. Then gases harden the sand within seconds. When the pattern is removed, you're left with a cavity shaped like the magnet. That sets the basic geometry for everything that follows. Alloy melting and homogenization. Here's the fiery part. Metals go into an induction furnace that can reach about 1700 degrees Celsius, hotter than some volcanoes. Unlike traditional furnaces, induction uses electromagnetic fields to heat the metal from within. The coil drives alternating currents that agitate atoms until the mix turns into a glowing soup. The goal is an even blend, so aluminum, nickel, and cobalt are distributed uniformly. Stirring, tight temperature control, and timing make that happen before the pour. If you see sparks or flames when the alloy hits the sand, that's trapped gases igniting. Cooling and solidification. Once the molds are filled, the metal cools. Workers break the sand molds with sledgehammers, exposing the hot metal to air so it cools faster. Rapid cooling, quenching, changes the alloy's microstructure. Cooling rate sets crystal size and arrangement. Tighter, finer crystals usually mean stronger, more reliable magnetic properties, while larger crystals can weaken performance. Getting this stage right is critical. Preparing for heat treatment. The solid pieces aren't magnetic yet. Workers collect and sort them, then set them up for heat treatment. Ring-shaped parts are threaded onto a copper pipe and placed in a tube filled with silica sand, which keeps them from shifting or warping as they heat. The tube is sealed with concrete, leaving the copper exposed to carry heat. Heat treatment for magnetic optimization. The sealed tube goes into a furnace and heats until it's red hot. Heat treatment is key. By controlling temperature and the heating and cooling rates, we tune the microstructure to boost coercivity, resistance to demagnetizing, and remanence, the strength that remains. Skip this step and the magnets would be weak or unusable. Orienting the magnetic domains. After heat treatment, the tiny internal domains need alignment. Think of billions of tiny arrows pointing randomly. They all have to face the same way. The rings go into a solenoid coil, where a controlled magnetic field penetrates the metal and lines up those domains for final magnetization. Machining and grinding. Many magnets need precision shaping for motors and sensors. Machining and grinding remove excess material to hit exact dimensions. The material is brittle, so careful handling matters. Diamond-coated tools and steady coolant help prevent cracks and overheating. Final magnetization. The real transformation happens in the magnetization chamber. Shaped, oriented pieces are placed between powerful electromagnet poles. The external field forces their domains to lock into alignment, turning them into permanent magnets. They'll stay magnetized unless exposed to extreme heat or a strong opposing field. Quality control. The future of magnets. Magnets aren't stuck in the past. Researchers are developing stronger, more heat-resistant alloys that rely less on rare earths like neodymium. Applications keep getting bolder. Maglev trains float above their tracks and can cruise around 310 miles per hour with almost no vibration. Magnets also power renewables. Wind turbines rely on them to turn motion into electricity. So the next time you stick a note to the fridge, remember, the same principles drive some of our most advanced machines. Got questions or thoughts? Drop them in the comments, your input matters. Share ideas for our next video and we'll give you a shout out. Thanks for joining us to explore the surprising stories behind everyday things. Don't forget to like, subscribe, and stay tuned for more. Want to keep learning? Click the next video right here.